So this is where we left off in the last lecture, and we talked about how to do electron configurations given this chart and how we would fill the various sublevels. And we talked about how the principal energy levels, 1, 2, 3, 4, 5, 6, 7, how this is the one closest to the nucleus, and this is the one further away from the nucleus. And we had the different shapes, the S, the P, the D, and the F sublevels, and how many electrons could be held in each one. So I'm going to show you an easier way today to find the electron configuration of an element, but what we're going to look at is using the periodic table. So this is just a general periodic table. Oops, let's go back to that. This is a general periodic table that shows you groups going down, periods going across. Let me just point out some things about the periodic table. So first of all, if you notice that in this group we have here, we have 7 different levels. So we have 7 different periods down this group, and the periods run this direction. Another thing I want you to notice is that there are 2 on this first one before we hit the trough. So we have 1, 2. These are the S sublevels. This is S1, this is S2. We have 6, 1, 2, 3, 4, 5, 6 going from left to right over here. So these are our P sublevels that are being filled. So this is P1, P2, all the way up to P6. Next thing that we would fill would be a D, and there just happens to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in this level. So and we're going to, these are our Ds, so this is D1 down to D10. And down here at the bottom, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This lanthanum and actinide came from the periodic table in D1. So these are our F orbitals here, F1 down to F14. So for example, let's say that I wanted to know, let's go to lithium. I want to know the electron configuration for lithium. Well, I could go back to our chart and follow the chart. I could also follow the periodic table. So I start with hydrogen at the beginning. So it's 1s1, and then this over here is going to be our 1s2. Because you notice that helium with 2 protons and 2 electrons really belongs right here, but because of its properties, it's put over here with the noble gases. So 1s1, 1s2, 2, this is level 2, this is S1. So our electron configuration is 1s2, 2s1, which is the same thing we get as if we did the periodic or the zigzag table that we did in the previous lecture. Let's pick another one that's further down, and I'll walk you through this again. Let's do magnesium. Magnesium has a total of 12. So we're going to start, we're just going to go left to right. 1s1, 1s2. 2s1, 2s2. Let's write those down. So 1s2, 2s2. We still aren't down to magnesium yet, so we just go left to right. So we go, this is level 2. This is P1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So 2, P6. We're going to go down to level 3. And this is S1, and there's magnesium, so it's 3s2. And we look at the number of valence electrons that magnesium has. We look at its highest principal energy level, which is 3, and all the electrons in it, which is a total of 2. And that's the valence number for magnesium. So it tends to lose those 2 electrons and become magnesium plus 2 when it reacts. Let's try another one. Let's try, for example, let's try manganese. Manganese. So we want to go all the way to manganese here. Let me go ahead and erase while I throw magnesium so we don't get them confused. So what we're doing is we have to just start at the top and account for where all the electrons are all the way up to Mn, which is 25. So 1s1, 1s2. We're going to cover the 2s2, then 2p6, 3s2, then 3p6. So we have 1s2, 2s2, 2p6, like an S, to 2p6 down to 3s2. We still haven't come across manganese yet. So we go to 3p6. And then we come down to the next one. There's 4s2. Now here's the difference. This level of D's, the first level of D's we have is in principal energy level 3. So while this is 4s2, this is 3D, 1, 2, 3, 4, 5. 3D, 5. And that would be the electron configuration for manganese. Now the zigzag table did the same exact thing. If you remember that once we did 3s2, we did 3p6. After 3p6, it went down to 4s2. And 4s2 went back up to level 3D and picked up 3D10, which is what this is. So this level of D's here, this level is 3, this level is 4, this level is 5, and this level is 6. Now we don't see the F sublevel showing up until the 4th principal energy level. So this is 4F, and this is going to be level 5F as we fill these in. This may take a little bit for it to sink in, and some of you are going to want to make sure you go back and do the zigzag instead of this one, but that's not a good idea at all. This is actually going to help you determine electron configurations faster. So you need to get familiar with this. Now that we've covered using the periodic table to determine electron configurations, I'm going to make your life a little bit easier. Because now that you know how to get the information from the periodic table, I'm going to show you another shortcut that's going to allow us to rely on the information given by our noble gases. Remember, these noble gases are noble because they have a satisfied octet rule in their outer sublevel, so they don't want to react or need to react or are pulled to react with another element necessarily. So they have complete outer shells, and everybody on the periodic table wants to be like the cool kids who have met the duet in helium's case or the octet rule in the rest of them. So we can go with those set electron configurations to help us do a shorthand of finding electron configurations of other elements on the periodic table. So let me show you an example of this. Let's say again that we wanted to do the electron configuration of magnesium. Well, we know that neon is the first noble gas before magnesium. So 1s2, 2s2, 2p6. So I could write down magnesium 1s2, 2s2, 2p6, and then we have 3s2. But this information right here, this electron configuration, is that of the noble gas before it. So what I could do is I can just write down magnesium, and then I'm going to put this bracket. I'm going to put Ne to represent the electron configuration of neon, and then 3s2. The cool thing about writing it this way is it makes it pretty obvious what your valence electrons are, because you can see the higher principal energy levels out here to the side. So 3s2, and that's our valence electrons for magnesium. Let's try another one. Let's do potassium. So I could write out 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. But if you notice, the noble gas right before potassium is argon. So I can shorten that, and I can say electron configuration of argon, and then I can write 4s1. I could do this for vanadium. Let's say I want to do vanadium. So I'm going to go backward. I'm going to say that's argon. So vanadium is argon, and then everything that comes after argon until you get to vanadium. So it's argon, 4s1, 2, so 4s2, 3d, 1, 2, 3. So it's a shorthand method, and we rely on our noble gases in order to help us write this shorthand method. I'm going to get rid of these, and we're going to look at, we looked at metals so far. Let's look at how to do a noble gas configuration using a non-metal on this side. So let's say, for example, that we want to write the electron configuration of chlorine. So what we're going to do is, just like with the metals, we're going to go backward, and we're going to go back to the noble gas that comes before chlorine, which would be neon. So chlorine will be written as neon, and then everything after neon until you get to chlorine will be longhand. So neon, this is 1, 2, 3, so 3s2, 3p, 1, 2, 3, 4, 5. Sorry, it's 3s2, 3p, 5. And that would be the noble gas configuration for chlorine. When we look at this, we know that chlorine, this is the highest principal energy level, 3 and 3, has a total of 7 valence electrons. And we knew that because that's in group 7 or 17. So these are our halogens. And we also know that chlorine tends to, in this whole row, tends to gain an electron and get a -1 charge. That -1 charge makes them electronically like the next noble gas. So if I wanted to know what the electron configuration is for chlorine, or I'm sorry, the chloride ion, if I added an electron to this, what would happen? This would become, let's just use a different color, maybe that'll help. If we were going to gain an electron and become negative, this would become 3p, be like argon, be 3p6 instead. So the noble gas configuration for the chloride ion is going to be argon. It's isoelectronic to argon. So even though writing it as in the red here, writing it as an element, we go back to the period, or to the noble gas before it. When we look at nonmetals that gain electrons, they become isoelectronically like the noble gas after them. On the other hand, the metals become like the noble gas before them. So let's pick on calcium, for example. So calcium, the electron configuration for calcium is going to be argon. And it's going to be 1, 2, 3, 4, S2. Okay, so what happens when I want the electron configuration for calcium plus 2? Because we know calcium tends to lose these 2 electrons and be more like argon before it. I just write calcium and brackets around argon. But that's telling me that the calcium ion is the same electronically as the argon atom is. So metals that are positive become more like the isoelectronically like the noble gas before them, while nonmetals that gain electrons become like the noble gas after them when we look at their electron configuration. Again, it's going to take practice. There's a picture in your book that may help you get to where you use this so much you know that, so I don't think this is going to be necessary, but this may help you just to maybe keep it clear as to where those different orbitals are located. And practice makes perfect on this.